This is the second video on spectroscopy, on the spectroscopy of aldehydes and ketones, and I'm going to build on our discussion from last time in the spectroscopy of aldehydes. So I won't go into quite as much detail in talking about the sources of each of these types of spectroscopy, but we will analyze the information they give us. So they give us information from a few different sources. First we have the mass spectrum, second we have the IR spectrum, third we have the proton NMR spectrum, and fourth we have the carbon-13 NMR spectrum. Those are the four sources of information. From the mass spectrum, we're going to get the molecular formula. From the IR spectrum, we're going to get the functional groups. From the H1 NMR and carbon-13 NMR spectrum, we're going to get how the atoms connect. Okay, so first the mass spectrum. We see that the M+1 peak is 4.4% as high as the molecular ion peak. As we discussed last time in the previous video on the spectroscopy of aldehydes, that means that we have 4 carbons. So we know in our molecular formula we'll have C4. So 4 carbons. Also, it says that the molecular ion peak has an MZ value of 72. That means that all the masses of the different pieces have to add up to 72 AMU. Now, so far, we know that we have 4 carbons. Each carbon weighs 12 AMU, so that's going to be 48 AMU coming from the carbons. So, the next thing we want to see is if we can fill in the rest of the mass with hydrogens. Now, in order to add the rest of the mass, we'd have to add 24 AMU to the 48 in order to get 72. Since each hydrogen atom weighs 1 AMU, that means we would need 24 hydrogen atoms. But there's no way that you can fit 24 hydrogen atoms on 4 carbons. The maximum number of hydrogens you'd be able to fit is 2 times the number of carbons plus 2. So here that's 2 times 4 plus 2, or 10. 24 is way more than 10. And so we can't just have hydrogen here. We must have another heavier element. Now, the next most abundant element on the Earth is oxygen. Think of all the water. Water covers 3/4 of the Earth's surface. And so again, we're coming up with a plausible molecular formula. This is something of a hypothesis. This isn't ironclad. And we're going to test this plausible molecular formula with the data from the IR, proton NMR, and carbon-13 NMR spectra. So if we have oxygen, which is probable because there's so much oxygen on the surface of the Earth, let's say we just had one atom of oxygen weighs 16 AMU. 16 plus 48 is 64. So that would give us 64, but we need 72. So to add up to 72, that means we'd have to have 8 hydrogens. So adding all of those up, we would end up getting 72 AMU. That means that the formula for the molecular formula will be C4H8 and O. So those subscripts are coming from the number of those elements that we have in order to get the correct molar mass, or molecular mass. Okay, so C4H8O. Now, next. So much for the mass spectrum. So we've juiced all of the information we could get out of that. We also can use this to get a sense of how many pi bonds or rings we're looking for. We can find the degrees of unsaturation. Remember, that's 1/2, 2 times the number of carbons, plus 2, plus the number of nitrogens, minus the number of halogens, fluorine, chlorine, bromine, iodine, minus hydrogen, the number of hydrogens. So that's 1/2 times here, 8 plus 2 plus 0 minus 8. And so that's just 1. So we have 1 pi bond or 1 ring. So that's all the information we could get from the molecular formula and from the mass spectrum. Okay, next the IR spectrum. It says that the IR spectrum of the same compound has a sharp peak at 1720. That's a sign that we have a carbonyl. And it says they have no peak between 2700 and 2850. That means that there is no bond from a carbonyl carbon to a hydrogen. It's not there, because that bond absorbs between 2700 and 2850. If there's no peak between 2700 and 2850, there must not be that bond. In other words, the IR data tells us that we have a ketone. Okay, well that certainly squares with the pi bond that we got from the molecular formula. So things are lining up. So far so good. We use the IR data to figure out we have a ketone. Okay, next. If we have 4 carbons, there's really only one place that the carbon could go. It's going to go on one of these sides. The molecule is symmetrical down the middle, and so it doesn't matter which side you put it on. This is looking like the only possible structure for that molecule. However, we do need to check, because maybe our original molecular formula was completely off. Maybe there was a nitrogen in here instead of an oxygen, or some other compound, or some other element mixed in. So if it truly is this, it should have certain features. Let me draw in the hydrogens. There are 3 hydrogens on this carbon over here. We would have 2 hydrogens on the carbon here. And we'd have 3 hydrogens on the carbon at the far left. Okay, one at a time. These hydrogens here. Next door, there are 0 carbons. So they're going to split into the n+1 rule. According to the n+1 rule, that will be 0 + 1, or a singlet. So those will be in a singlet. For the shift, CH3s normally appear at 0.9 parts per million, but it's alpha to a carbonyl, so you add 1, and you should get 1.9 parts per million for that. And the integration should be 3 hydrogens. Okay, next. These hydrogens here. There are no hydrogens to the right of them. There are 3 hydrogens to the left, so they're going to split according to the n+1 rule. That'll be 3 + 1, or 4. They're going to split into a quartet. The shift for these, CH2 normally shows up at 1.2. It's alpha to a carbonyl, so you add 1, and it should show up at around 2.2 parts per million. The integration will be 2 hydrogens. There are 2 hydrogens in that electronic environment. Okay, last, the green. This has 2 hydrogens next door, so it's going to split into 2 + 1, or 3 peaks. In other words, it will be a triplet. Now, CH3 normally shows up at 0.9 parts per million. This is beta to a carbonyl, so we'd add 0.2, so that gives us 1.1 parts per million for this electronic environment. The integration should be 3 hydrogens. That's how many hydrogens are in that electronic environment, 3. Okay, so we can check this data, see if this is the correct structure. It says the H1NMR spectrum of the compound has a singlet at delta equals 1.9 parts per million with an integration of 3. A quartet. And if we had read this first without having any idea what the structure is, seeing a quartet and a triplet is the sign of an ethyl group, so things are looking good for this ethyl group over here. We have a quartet at delta equals 2.2 parts per million with an integration of 2. Quartet at 2.2 with an integration of 2. And a triplet is 0.9 with an integration of 3. So that's close. We have 1.1 here with an integration of 3. Technically, it should be 1.1. When you do the NMR spectra, sometimes the shifts will be slightly off. But they should be around where they're said. And technically, this one should be 1.1. Okay, so that data seems to match on the whole. Also, we have the carbon NMR data. Carbon-13 NMR, there's 4 peaks. That means you would have 4 different electronic environments for the carbons. And that seems to hold good. We have a carbon in the carbonyl, that's 1. We have carbon, a CH3 right next door, that's the second one. We have a CH2 right next door, so that's a third one. And finally, we have a CH3 2 carbons away, that's a fourth electronic environment. And so that, you have 4 electronic environments there, so you would expect 4 peaks in the carbon-13 NMR spectrum. In other words, this structure fits all of the data that we would expect for this molecule. And so the structure for this molecule will be like this. It'll be 2-butanone. So this is the structure that you get from all of these readouts from these machines. And once you have that structure, you can think through all the conceptual steps of synthesis that we've learned in previous chapters. All right, one last one. We have the mass spectrum of the compound. That's going to give us the molecular formula. We see that the n+1 peak is 5.5% as high as the molecular ion peak. That means that we have 5 carbons. So if we're thinking about organizing this, we have 5 carbons. Each carbon is going to weigh 12 AMU, so that's going to be 60 AMU coming from the carbons. Okay, next. The molecular ion peak has a mass-to-charge ratio of 86. That means all the mass of everything has to add up to 86 AMU. Okay. If we tried to add hydrogens, so we know that we're going to have C5, if we tried to add hydrogens, we would have to add, just hydrogens, we would have to add, we know each hydrogen weighs 1 AMU. We have 60 now, we need 86, that means we'd have to add 26 hydrogens to get the total 86. But there's no way you can fit 26 hydrogens on the carbon. At most, you can fit 2 times the number of carbons plus 2. So here that would be 10, 2 times 5, plus 2 is 12. No way you can fit 26 hydrogens on those 5 carbons. What that means is that we must have another element. So let's try the most abundant element after these carbon and hydrogen. That's going to be oxygen. Actually, oxygen is much more abundant than carbon, but we know that we have 5 carbons because of the n+1 peak. Okay, well, if we have 1 oxygen, that would bring 16 AMU, and so that would be altogether 76. We would need 10 more to get our total. That means we would need 10 hydrogens. 10 hydrogens can fit. And so this is a plausible molecular formula, C5H10O. Now, we can find out the degrees of unsaturation. It's going to be 1/2, 2 times the number of carbons, plus 2, plus the number of nitrogens, minus the number of halogens, minus the number of hydrogens. So that's going to be 1/2 times 10, because the number of carbons is 5, plus 2, we don't have any nitrogens, we don't have any halogens, we have 10 hydrogens. So that's going to be 1, right? 1/2 of 12 minus 10 is 2, 1/2 of 2 is 1. That means that we have 1 pi bond or 1 ring. So that's all the data we can squeeze out of the mass spectrum. We get a plausible molecular formula, and we know the degrees of unsaturation associated with that molecular formula. Next, IR. We're going to get the functional groups from the IR spectrum. It says that we have a sharp peak at around 1700, 1710. That means that we have a carbonyl. But at this point, it could be an aldehyde or a ketone. The next thing we see is that we have no peak between 2700 and 2850. That's the range where a carbon to hydrogen atom, or carbonyl carbon to hydrogen bond would absorb. Because we don't have that, we don't have that bond. In other words, this must be a ketone. If you have a peak in this range, then you have an aldehyde, and if you don't, then it's a ketone. That's if it's combined with a sharp peak around 1700. Well, that takes care of 3 of our carbons. But now we have to figure, so much for the IR spectrum. We can see that that's corroborating our molecular formula, which gives us 1 degree of unsaturation. It doesn't prove it, but it's supporting it. All right, well, we've used 3 carbons, now we just have to use 2 more. There are several ways that we can have this. So let's look at the hydrogen NMR data and see if we find any patterns that shoot out at us. It says the proton NMR spectrum of a compound has a quartet at delta equals 2.2 parts per million with 4 hydrogens. Well, that's strange. We're not going to have 4 hydrogens on 1 carbon. And a triplet at 1.1 parts per million. Integration is 6. These large numbers for the integrations are suggesting that we have the same electronic environment for 2 different carbons. That's the only way we could have 6 hydrogens in the same electronic environment, is if they're on 2 different carbons. But for 2 carbons to have hydrogens in the same electronic environment, there has to be symmetry. Okay. The other thing you'll notice is we have a quartet and a triplet, and that is a giveaway for an ethyl group. So the way we can get symmetry and an ethyl group is if we add the 2 carbons that are left, 1 on each side. Notice we have an ethyl group on the left and an ethyl group on the right, and those are symmetrical. Because it's symmetrical, the hydrogens on this first carbon are the same as the hydrogens on the other side. And the hydrogens on the end carbon are the same as the hydrogens on the end carbon on the other side. So we really have 2 electronic environments in this possible structure. We have the blue one right next to the carbonyl and next to a CH3, and we have the orange one at the end of a chain next to a CH2 and then a carbonyl. Okay, well, let's see how this plays out. Let's think about the types of peaks that this would have. We're just going to look at one side because the 2 sides are going to be the same. So I'm going to look at this right side here. These hydrogens are next to 2 hydrogens. They have 2 hydrogens next door. So they're going to split into, using the n+1 rule, into 2 + 1 peaks. So 2, the number of neighboring hydrogens, plus 1. In other words, it will split into a triplet. So that's going to be a triplet. If you think about the shift, a CH3 usually appears at 0.9, but it's beta to a carbonyl, so it should appear at 1.1. You add 0.2 when you're beta to a carbonyl, so that's 1.1 parts per million that we would expect for the shift. And of course, the integration value, now this is an interesting thing. The integration value for this individual set of hydrogens would be 3, but because we have another set of hydrogens in that same electronic environment, we'd have to add those together because they're going to show up in 1 peak, and the integration would be 6. All of the hydrogens in that environment, and there are 6 of them in this molecule. Okay, now if we think about the carbons next door, those have no carbons to the left and have 3 carbons to the right. And so they're going to split into, using the n+1 rule, 3 carbons next door plus 1, they're going to split into a quartet. You'd have a quartet. Now CH2s normally show up at around 1.2. They're alpha to a carbonyl, so you'd add 1. And so you'd expect the signal to be at 2.2 parts per million. And when you think about the integration, there are only 2 hydrogens here, but notice there are other hydrogens in the same electronic environment. Those will all show up in the same peak. And so there are actually 4 hydrogens in that electronic environment. Now let's check to see if this matches with the data they give us for the proton NMR. At first, it says we have a quartet. Okay. The quartet has a shift of 2.2 parts per million and an integration of 4. Quartet, 2.2 parts per million, integration of 4. Then it says we have a triplet at 1.1 parts per million, integration of 6. Triplet at 1.1 with an integration of 6. Finally, we can check to see if this matches the carbon NMR spectrum, because it seems so far everything is fitting in. So far, this matches the mass spectrum, the IR spectrum, and the proton NMR spectrum. It says the carbon NMR spectrum has 3 peaks. That means you have carbons in 3 different environments. You have a carbonyl carbon. That's one environment. You have carbons right next to that on either side, wedged between a carbonyl and a CH3. That's a second environment. And you have the carbons on the ends, CH3s that have a CH2 and then a carbonyl on either side. In other words, this structure has 3 electronic. It has carbons in 3 electronic environments. And so the carbon-13 NMR spectrum has 3 peaks to reflect those 3 electronic environments. And so the structure of this molecule overall will be 3-pentanone, a structure that we used a couple times in our synthesis problems. And so if you wanted to check whether you actually had made that molecule at that step of the synthesis that we talked about, you could have done mass spectrometry combined with IR spectroscopy, proton NMR, and carbon-13 NMR to confirm this beautiful structure. So in this video, we have piggybacked off of our discussion of the aldehyde spectroscopy. We went into a little more detail there about the techniques behind these numbers. In this video, we've just used the numbers, assuming that we covered the concepts behind them in the previous one. So we used the numbers to verify and to elucidate these ketones. Notice that the one difference between these structures, which are ketones, and the previous structures in the previous video, which were aldehydes, is that these structures had no peak between 2700 and 2800, the ketones, whereas the aldehydes had a peak in that range. So hopefully these problems help with figuring out the structure of a molecule based on spectroscopy.